share my screen?
Yeah, you can share the screen.
Okay.
So Vanessa Bohm is a postdoctoral researcher at UC Berkeley, working at the interface of cosmology and machine learning. And she's going to talk about anomaly detection with the probabilistic autoencoder. Please, Vanessa, take it away.
Okay. Yeah. Hi, everyone. Thank you very much for the invitation. Really glad to be here. Just before we start, is that okay? Do you see my slides? Does the slide change work? And do you hear me fine?
Let's see if I can you try switching the slides?
Yeah,
okay.
I saw it. It looked good. Yeah.
It looked good? Okay, awesome. Thank you very much. Okay. So the title of my talk is Anomaly Detection with the Probabilistic Autoencoder. So there will be basically two parts. First of all, I want to talk about the general problem of anomaly detection and how we can leverage machine learning to do that. And I think this is going to be applicable to all kinds of scientific applications, to all kinds of scientific domains. And then with this, I want to introduce a deep learning model, the probabilistic autoencoder that I have developed. So my background is astrophysics or cosmology. So I will be taking a little bit of the lens of the astrophysical perspective, and I will also use an example from astrophysics in anomaly detection. And this photo here has nothing to do with my talk. The only connection is that I wanted, because this is an intercontinental workshop, I wanted to give you some hint about where I'm giving this talk from. So this is Berkeley and the Bay Area. So coming to astrophysics and machine learning, just like in every other scientific field, the number of publications that mention machine learning and astrophysics has skyrocketed in the last couple of years, as you can see here. And I mean, on one side, this is exciting, but on the other hand, I think this also raises a lot of questions about how we want to use machine learning and when we should be using machine learning in astrophysics. And I guess you all follow XKCD. So XKCD has this very fun little summary of the general criticism that people have with machine learning. So there's this guy who asks, oh, so is this your machine learning system? And the person answers, oh, yep, you pour the data into this big pile of linear algebra, then you collect the answers on the other side. So what if the answers are wrong? Well, you just stir the pile until they start looking right. So this is, of course, a very low-level criticism, but I think we can learn from this, or what we deduct from this is that we can come up with formal requirements for when and how we want to use deep learning or machine learning in general in scientific applications. And these points are taken from a summary or a little list that I put up a couple of years ago for my students for best practices of machine learning. So the first point, which seems pretty obvious, is that when we want to use machine learning in science, is we want something that is reliable and numerically stable. And this seems super obvious, but we will see in a couple of slides that this is not always given, and that actually we can have numerical instability and reliability issues in applications that we think are very straightforward. Another major point is that we, as scientists, don't only care about answers, or an answer for us is only an answer if we only know how certain we are of that answer. So we need probabilistic models, and we need uncertainty estimation. And I think this is one of the big challenges in machine learning, because a lot of, especially deep learning models, struggle with providing accurate uncertainties. Then tasks we can't solve otherwise. I think a lot of the spike is fueled by publications where that are proofs of concepts, where deep learning is applied to problems that we can already solve optimally. So we really want to find that niche where machine learning can be applied to problems that either we cannot solve otherwise, or where we can get a significant computational speed up with machine learning. Interpretability and verifiability, I'm putting both of them here because I think a lot of times people get really obsessed with interpretability. But I personally think that interpretability is not as important as long as we have verifiability. But that's another point that we want to satisfy. And then last, I have little fine-tuning and easy use. So I assume that a lot of people here in the audience have trained machine learning models before. And one of the things that you probably know then is that training a machine learning model is more of an art than a science. So usually what you have is you have lots of hyperparameters that you need to tune. You often need background knowledge to actually make this model work. And you usually cannot just take it off the shelf and apply it to your problem. And as a practitioner, as a scientist, you're interested in your specific scientific application, and you're not so much interested in becoming an expert in this specific machine learning tool just to be able to use it. So we if possible, we want models that are easy to use. So looking at all of these points, especially the probabilistic model uncertainty estimation, we have this one class of deep learning models that stands out as particularly interesting for us, and those are deep generative models. Because deep generative models are inherently probabilistic. They learn the probable distribution of data, and they can, that's why they're called generative, they can sample from it. So if you have some training data, you present it to the model, it learns some representation of that probability distribution, some estimate, and then it can sample from it to generate new data that it has never seen before. And many of these models also have the capability to evaluate probabilities. So to perform density estimation, if you present a new data point to it, it can tell you this is a likely data point, and that's the less likely data point. So with this property, these models seem just made for anomaly detection, where very easily you give it a data point. If it gets assigned a low likelihood, you say, okay, this must be an anomalous likelihood. So this seems straightforward. However, it turns out that these models can catastrophically fail in this. This was a paper a couple of years ago by people, I think from Google Brain, that asked if generative models know what they don't know. And they found that for certain combination of data sets, that a model, for example, here trained on fashion and mist would assign higher likelihoods to outlier data from the MNIST dataset. And they found that this applied or was true for all kinds of different generative models, including variation autoencoders, normalizing flows, and pixel CNNs. So what is behind this? Obviously, this is very worrisome. And the fact that this only applied to certain data sets gives us a first clue. So looking at fashion MNIST and MNIST here as an example, when you do PCA analysis, what you find is that they actually live on a lower dimensional manifold. So you need much less PCA components than you have degrees of freedom in a data set to explain most of the variance in these data sets. And when you look at this in terms of eigenvalues, the non-commutative plot, you see that you have this vast amount of eigenvalues that are extremely small and that at the same time basically that don't describe anything in your data, but they're still there. And we know that small eigenvalues in data covariances are problematic for several reasons. The first reason is that they're very difficult to estimate. This is why you have all of these shrinkage methods and so on that try to correct the fact that you get these very small eigenvalues, usually wrong if you try to estimate them from a finite data set. Also, they lead they lead to numerical instabilities. And while they're causing all of these problems, they're completely uninformative because there's basically no information about the data set contained in this. So if you now come up with a very simple toy model for a data likelihood, which is saying, okay, let's just use a Gaussian, describe our data as Gaussian distributed and estimate the mean and the covariance from the training data, then you will find that this Gaussian, this multivariate Gaussian will be dominated by those very small eigenvalues, which are probably wrong and at the same time are completely uninformative. So because of this, this is why we use PCA, probabilistic component analysis, and there is a probabilistic version of PCA that was introduced by Tipping and Bishop in 1999, which is basically performed in two stages. Stage one is a normal principal component analysis on the training data, where you then discard the small eigenvalues that are non-informative. And this principal component analysis gives you a data model. It says that your data actually lives or is very well described in a lower dimensional latent space Z, and you get a relation between Z and X, which is an orthogonal linear transformation, and the eigenvalues that you've discarded are treated as noise. So now you can, on top of this data model, you can put a probabilistic interpretation and perform a density estimation by basically approximating, saying that this noise is Gaussian distributed, and also saying that the prior and latent space is a Gaussian. And this then gives you probabilistic PCA. Notice that we have two ways with probabilistic PCA. We have two ways to perform density estimation. We can either perform density estimation in the latent space, where we just ask how are the Z's distributed, or we can perform density estimation in the data space, where now basically the covariance is now regularized by this noise component, by this Gaussian noise component. So if we use probabilistic PCA to get a density estimation, and we go back to our example from the beginning, where we train on the fashion MNIST data set, and we use the MNIST data set as an outlier data set, and then do density estimation to separate the two data sets. This is what we get. So in this plot, what I'm showing is the area under receiver operator curve. Basically, this is a metric of how well we can separate the two data sets. Higher is better. If it is 1, then we can perfectly separate the two. If it is 0.5, then we've just flipped the coin and it's random assignment, and everything that is below 0.5 switches and gives a biased result, a wrong result. And so I'm plotting the ROC here as a function of PCA components, and I'm plotting it both for density estimation in latent space and for density estimation in data space. And what you see is that both of them actually get their peak and get their best outlier detection accuracy at lower number of principal components than the actual data dimensionality. And as we go to higher dimensionalities, that the accuracy, the outlier detection accuracy actually decreases. So the best one that we get is an ROC of 0.98, which is fairly good, way better than the catastrophic failure that we observed before with the nonlinear models at 127 components. And this is for the density estimation in latent space, which it's just like here, I guess this is just an empirical observation that the density estimation in latent space produces higher accuracy. So with these observations, the question is, can we bring probabilistic PCA into the nonlinear regime? Can we generalize this? And the answer is, of course, yes. And this is what we call the probabilistic autoencoder. So in stage 1, what I'm using is a simple autoencoder that has been around for quite some time. And the autoencoder is really a generalization of PCA in the sense that PCA finds among the class of linear models, it finds the linear model that minimizes the reconstruction error. And the autoencoder finds the model that is trained to minimize the reconstruction error among the nonlinear models that can be that are defined through the network. And so the autoencoder takes the data and compresses it to a lower dimensional latent space, and then has a decoder that brings it back into the data space. We have, just like in the PCA, there's some reconstruction error between the two, and we can now operate in the lower dimensional latent space that has gotten rid of the singular directions and dimensionalities that we think were the reason why the generative models were struggling with the anomaly detection. So if I now run density estimation on this latent space distribution, what I find is that the anomaly detection for this example that catastrophically failed actually works, and it works very well. I didn't put the numbers here, but we get 0.998 for the ROC, which is basically with an error bars compatible with 1. So perfect separation between in distribution and out of distribution data. So this is the anomaly detection solved, but of course the probabilistic autoencoder is more than that. Here I only said that we are doing a density estimation, but this density estimation is actually performed with a normalizing flow that takes the latent space density distribution, latent space distribution of the autoencoder and Gaussianizes it. And so with this, we actually also make a generative model, because now we can sample from this Gaussian distribution, bring the point that we sampled in the Gaussian space into the autoencoder latent space, and then decode it to produce samples. And so these are examples for the CellLab-A data set. These are generated images, generated faces that the model has never seen before. And going back to my introductory slide, I just want to point out that we've had very little fine-tuning here and a model that was extremely easy to train, because an autoencoder is very easy to train and usually works out of the box. Sometimes there's a little bit of concerns with overfitting, so you need a little bit of regularization, but that's usually pretty easily achieved. And then the second part is the density estimation in latent space. And because we are operating here in lower dimensional latent spaces, depending on the data set here, I think I used 64. And training a normalizing flow is much easier, and you need a less complex density estimator in these lower dimensions. So it's very easy to set up and train. We also gain, with this approach, we also get a latent space without any holes that is very continuous, which you can show by bringing data points, test data points into the latent space, into the Gaussian latent space, connecting them with a strain line, and then sampling along this line. And what you can see is that we get very smooth transitions from one image to the other. And this is important when we think about applications where we want to apply this, for example, where we want to use this for corrupted data, use it as a prior for corrupted data, for example. There is a certain catch here. So this model seems very simple and works extremely well for its simplicity, but really the secret is the normalizing flow, because not any density estimator does the job. So normalizing flows are so successful because they have amazing generalization properties. And this is, and the way to illustrate this is by looking at the nearest neighbors of generated samples. So here I'm using PAE with a normalizing flow density estimation. These are samples generated with it. And these are the nearest neighbors in the training data. And while there is some similarity between some of them, they usually differ, all of them differ in the details. So these are new samples. Some of them aren't even similar, but some of them have a little bit of similarity. But those that have, like this one here, they differ in the details, or here the heel is different, for example. If I do the same exercise with a kernel density estimator instead of a normalizing flow, what I find is that the kernel density estimator does not smoothly interpolate, it does not generalize well, and that the generated samples are really similar to training samples. So that what the kernel density estimator does is it kind of like starts fitting delta functions, even though, of course, this is prohibited by the training and by the cross-validation, but it has a tendency to memorize the training data. So we get points that are clearly just extremely similar to the training data here, like these shoes, for example, or this t-shirt. So with this, I want to come to the summary of the more machine learning parts. So I've introduced the probabilistic autoencoder as a nonlinear generalization of probabilistic PCA. We first trained it to minimize the reconstruction error, and this is actually different, for example, to a variational autoencoder, where you optimize both basically the density estimation in the latent space and the reconstruction error at the same time in one training step. Here, what we do is we first reach the optimal reconstruction error, and then we perform latent space density estimation with a normalizing flow. So this means that we can first get a really, really good reconstruction error, and then we can focus on getting the density estimation right. And because of this, it outperforms a variational flow with a flow prior in reconstruction quality, and it also achieves comparable sample quality and is easier to set up and train. And we've also seen that the latent space density estimation provides excellent outlier detection accuracy. So with this, I want to move to some application in astrophysics. Specifically, what I'm working on right now is as part of the dark energy spectroscopic instrument collaboration, the Desi Collaboration. So Desi is a spectrograph that is currently observing, and by the end of the observing time, it will have observed 45 million objects in the sky. And for each of these objects, it will produce a high quality spectrum. And here I'm showing some examples of what these spectra look like. As you can see, they're super high. They're very different, so very diverse. For example, starburst galaxies have these really strong emission lines. Normal galaxies, or more regular galaxies, have more of a broad emission with some absorption lines. And then stars, for example, have a black body spectrum. So there's a very wide variety in different objects that we observe here. And because we're looking at 45 million objects, there's just no way that someone's going to sit down and go through all of them and look for things that are interesting. So one task that we have here is to mine this data for interesting objects. And interesting objects can be, for example, supernovae, which are star explosions that are transient. So they just happen and we can't really plan for them. We can't really plan for observing them, but we kind of have to be lucky to capture one by chance and then find it in this huge data set. But also just quirky galaxies and so on. So there's lots of different things that could be interesting about these spectra. So for this, we can now use the PAE. So we have now more complicated real world data, which is incomplete. So we have mass here, we have noise in these spectra. So we actually do some modifications to the autoencoder so that it becomes denoising and that it's able to deal with the mass. So it actually, in the reconstruction, what it does is it produces a denoise spectrum that also inpaints the masks. And the latent space distribution here, so we are using a 6-dimensional latent space distribution. This is just a projection in 2 dimensions. And this is just to illustrate how different types of galaxies with different properties. So we saw the starburst ones before that have these strong emission lines. There are also some with broader emission lines. There are some with active galactic nuclei. So there these different features or different spectra actually already get organized into different places here. And then there are some spectra which we can already see by eye that are clearly outlying. So when we now perform density estimation on this, we can look at what are the most common spectra and what are the most uncommon spectra. So the most typical spectra, and I have to say this is work in progress, and also this is not Desi data. This was SDSS data, so this is from an earlier survey. This is just while we are setting up the pipeline. So these are the most typical spectra. These are the kind of spectra that we saw before. We have a different scaling here, but these are basically these broad emission galaxies that then have absorption and emission lines on them. And the most unlikely spectra, I mean, you don't need to be an expert to see that they're clearly very different from these most typical spectra, and they're also none of the spectra that I showed you before as typical examples. So what we have here, and this is now the next task to separate them. So the first one is clearly just a bad spectrum that has been saturated in one of the lines. So this is kind of like a useless data point that needs to be cleaned up. But then we also have these guys here. And what we see here is that we have broad emission lines, which means that there's some velocity structure. But on top of that, we also have some additional features on top of these broad emissions, which means that there's some unusual velocity structure here going on. So there are some dynamics in these galaxies that are interesting or untypical. And this guy here could actually be a galaxy hosting a supernova, but this is something that, you know, has to be evaluated and confirmed in several steps. So with this, I'm already, I think I'm gonna stop here because I know that we are running late and on the general schedule. So this is just to give you an example how this PAE anomaly detection also works with messy real-world data sets. And I think I'm gonna use the remaining time for questions. So thank you very much.
Thank you, Vanessa. So are there questions from anybody? You can just unmute yourself.
Hi, Vanessa, this is Kyle. It's a great talk. I think it's very, it's super useful. And I'm curious if you've run into situations where like the kind of, dimensionality of the data manifold is not, there's maybe some part of the data that wants a different dimensionality than another, and you might want some kind of like, piecemeal type of approach. What kinds of thoughts you've had about that, or if you haven't run into situations where that's necessary?
So you're saying where parts of the data, okay, so and then I hadn't actually, I haven't run into any of these problems. So what do you think would happen in anomaly detection then? That part of the data would get assigned, that we just would mess up anomaly detection for part of the data, but not for the other part of the data?
Yeah, or so, I mean, I don't know. I mean, certainly like in some particle physics situations where you have like energy and momentum conservation, one type of process will like literally be sitting on a manifold of some dimensionality. But if there's another, intermediate particle there that's decaying or something, then it will be the phase space is a different dimensionality. And so, so my picture in my head is somehow that there's kind of like a mixture model of different kinds of distributions that have different intrinsic dimensionality. I don't have a good solution for it, but it's just something that we've thought about. I was just curious if you had any thoughts.
No, it's a good point. No, I haven't actually run into any of these problems yet, but yeah, it's an interesting thought. Yeah.
Any other questions before we stop for a break? Well, if not, then thanks a lot, Vanessa. And then let's reconvene in 10 minutes for Kyle for the last talk. Thank you.